every hydraulic element in the model is basically a boundary condition in any node element, really, and that's basically described as a series of mathematical equations describing that particular node element. So there's a lot that goes behind, say, the pump element. So as there's a change occurring in the equations the hammer is solving, once it reaches that element, there's some additional equations behind that element that determine how it reacts to that. So how I pump, what will the pump do, and what effect that has on the other results. So things like a pump shutting down and how that impacts what happens in the pipes next to it. So every element in WaterCAD or WaterGems has a hammer equivalent. So anything that you can model in WaterCAD or WaterGems, you model in Hammer. But Hammer has some additional elements that really are only used in Hammer. So things like, you can see in the screenshot at the bottom, towards the right side, there's transient specific elements that you could include them in WaterCAD or WaterGems ahead of time so that you have that all filled out before you do the transient simulation. But really, they're there mainly for Hammer. So things like air valves, surge tanks, discharge to atmosphere, they tend to be used and have a bigger impact when you're dealing with transient simulation. So types of boundary conditions. I won't go into too much detail on this. This is pretty much self-explanatory, but you have ends of the system that are your boundaries. So you're maybe a demand at the end of the system, or a dead end at the end of the system, or a reservoir at one end of the system. So that's your sort of boundary condition there that determines your hydraulic grade or your flow. Flow control is something that will adjust the HGL. So you have your orifices that might have a head loss through them. There's a couple of different types of orifice elements, and then you have your active valves, like a discharge to atmosphere configured as a valve, throttle control valve, various types of valves that you can use. Then surge control, these are the elements that are primarily used to mitigate the effects of your transient. So things like air valves at your high points that will let air in, surge tanks, and the big one is really gas vessels, also known as hydropneumatic tanks, do a pretty good job at surge protection. There are a few others. And rotating equipment, that's mainly your pumps and your turbines. Some additional terminology. So here's a sketch here that shows some terminology about when we're referring to specific points along a system in Hammer. So in WaterCAD and WaterGems, you have results at your pipe and results at your node, right? In Hammer, it's a little bit different. So at a particular node, so like, for example, this point right here where the three pipes are meeting, you might have a junction there. But Hammer, when you're looking at Hammer transient results, you're not really graphing, say, pressure at that exact junction. You're graphing the pressure at the end point of the pipe that meets that junction. And this is mainly because of the interior points that Hammer is calculating at. So, as we mentioned before with the method of characteristics, we're, computing all these equations not just at the endpoints, but all along the pipe. So you really have a result at the end of this pipe, and a result at the end of this pipe, and the result at the end of this pipe where it meets that junction. So when you're looking in Hammer in the transient results viewer, you'll see something that looks a little bit odd, and I'm going to switch over to Hammer to show you what I mean. So if I look in the transient results viewer, when you're looking at time histories, you might notice, well, when you're picking a certain element, it's the name of the element colon a name of another element. So P3 colon JNC. So what this is showing you is that's going to plot results at the end of pipe 3 right here, at the end of it next to this junction. So you're basically graphing at this junction, but specifically at this end of the pipe. And that's more significant, especially for things like pumps. So if we look at P2 colon PMP, we're talking about the discharge side of the pump. Whereas, and I don't have it included as a report point, but if you wanted to look at the suction side of the pump, it would be P1 colon PMP. So just a terminology thing there. It's a little different from WaterCAD and WaterGems. So what should you model using Hammer? It's ultimately up to you, but what you really normally will be doing is first taking a look at just your normal operating conditions. Starting up your pump, maybe it ramps up a little bit. Maybe you're shifting speed of the pump. Maybe you're opening or closing a valve or hydrant at a reasonable rate, or your standard rate, and then see if your normal operating conditions are or would be a problem as far as transients. And then you'd model infrequent operations like pipeline refilling after maintenance, and that's a little bit of a complex topic when you're introducing that quantity of air. It's a bit of a specialized case. You would have a discharge to atmosphere at the end of your system with an initial air volume, and you might be analyzing what happens when all of that air is expelled. So that would be an infrequent operation. And then really you want to also be analyzing for those rare emergency operations, such as failure of equipment, emergency pump shutdown, valves failing in some way that causes them to instantly close, or operator error that could result in valves being closed too quickly. And then things like pipe breaks, where suddenly you have it's very similar to opening a valve too quickly. You want to model those rare conditions as well to make sure that you've assessed if they will have a problem. And then you want to examine the results for the impacts on several different things. So as far as safety, brakes, wear. So if you're seeing maybe the transient maximum pressure does not really get to the point where it would burst the pipe, but maybe it, from the cycles of a low and high pressure, it will, induce some wear and tear on the pipe or the pumps. That's something to consider. Then if you have negative pressures or sub-vapor pressures, you have to consider what's in the soil around that. Is it going to suck in some contaminants? If the pipes are moving, if you have significant transient forces that will move the pipes, what effects would that have? So when we're talking about stopping, starting, and shifting flow, you would use the pump element there for your pump starts and stops. Basically, what we're saying here is that fixed speed motors start flow fast usually, but if you have a soft start motor, that can help control the ramp up. So you have to consider what type of pump are you modeling here, and how fast will it start up or stop. When you're looking at the pump type transient, this is where you specify what the pump is going to do. Let me make this a little bit bigger for you. So this is where you specify, I'm modeling an emergency shutdown, I'm modeling a pump start, or I'm modeling some variable speed event where I'm putting in a pattern of pump speed over time. So maybe it's just going from a low speed to a high speed. So this is your everyday operations. For valves, opening and closing. So we'll talk a little bit more about this later. I don't want to go into too much detail now, but there's some very complex modeling capabilities when it comes to valves in Hammer. So it is very important that you take the time to fully understand those capabilities and their assumptions as far as modeling, the throttling of a valve, a valve closing or moving in some position. There's a lot of different ways you can do that. So for a normal operating conditions situation, it would just be a matter of how fast that change is happening in the pattern that you set up for that valve, which you assign to the valve. Firefighting, usually you need quite a large volume of water at a high velocity when that occurs. So what you have here is sort of the opposite of a valve closing. You have a sudden valve opening, basically, and there can be a transient as a result of that, a downsurge that occurs. So the operators need to be very careful not to open or close those valves too quickly. So that's something that you can model as, here's one scenario where valve is being opened too quickly, and here's a scenario where here it's being closed too quickly, and you can try different speeds and things like that. We talked about that. Yep. So how to model using Hammer? So things to focus on. So this is the basic process here. So first you decide on your simulation duration and the calculation time step. You enter your liquid properties, your pipe properties, basically your initial conditions. You get all that set up. Describe all those hydraulic elements, the pipes, the nodes. Establish which report points you want, so which areas in the model you want to be able to report those transient results at. Set up your profiles that you want to be analyzing in the transient results viewer, and then go ahead and compute the results and scrutinize them. And from there, you kind of react with maybe setting up several different additional scenarios where you might either test the sensitivity to certain parameters or try some what if situations. What if I do this? What if I do that? As far as the time step goes, one of the important concepts that we need to touch on here is the way that Hammer uses a time step along with the length of the pipe and the wave speed. So Hammer tries to have a wave be able to travel from one end of the pipe to the other in even multiples of the time step. So in order to accomplish that, sometimes Hammer has to adjust the length of the pipe to allow this to happen. There's an example on this page. Yeah. So if we have a pipe that's say 1,800 feet long, wave speed is 4,000 feet per second, time step is 0.1 seconds. Then what we have here is it's basically breaking it, within 0.1 seconds, within one time step, this is where the wave travels. And the next 0.1, this is where it travels, and the next one, and the next one. But that last one does not coincide with the very end of the pipe. So we can't calculate a result there. So we have to adjust the length of that pipe to line up with that time step, basically. So you might have an adjusted length here of, say, 1,600 feet, so that based on the wave speed and knowing that the calculation time step is 0.1 seconds, at that wave speed, it will reach the end of that pipe in an even increment of that time step. So you have, at the start of what we're looking at, we're at one end, and then 1, 2, 3, 4, we end up right at the very end of that pipe. So what you'll sometimes see is the notification that I have at the bottom of the slide here that says wave speed or length approximations deviate excessively from the entered value. So this is a very common question from a new Hammer user. What does this mean? So this means that basically you have some pipes that are being adjusted excessively just based on the wave speed, length, and time step. So that could mean that either your time step is too large or your pipe lengths are too small. A lot of the times modelers will include really small pipes that may have just been left over from WaterCAD or something like that. And if it's really, really short, then and say your time step is 0.1 seconds, then based on that wave speed there, you're going to see, you can tell how much that pipe will have to be extended to be able to meet that requirement. And if that adjustment to the length by default, if that adjustment to the length exceeds 50%, so if the new length is 50% or more compared to the original length, then it will generate this notification. And there is some control over, you can change that 50% to something else, but it's a pretty good rule of thumb. 50%. It at least alerts you to take a look at what exactly those adjustments are, which you can do in the pipe flex table, and decide if you're okay with that or if you really need to make some change. And the change being usually a smaller time step, or maybe combining that pipe with a nearby pipe so that it's not, you're not left with these tiny pipes, because they may not, you may not need to have such tiny pipes. It might just be a modeling artifact or something left over. If the pipes really are short, then sometimes you really do need to, check to make sure that, with those short pipes, the transients are not going to be a problem, or you need to be able to accurately assess what happens in that situation. So if there are cases where you really need to have those pipes stay short and basically have the wave travel and reflect how it really would, then what that really means is that you need a small time step. So in order to prevent excessive adjustment to that pipe, you have to have a smaller time step. So a typical time step, the default, I forget what it is, but the one I see used most often is about 0.01 seconds is usually a good one, and that's usually a good sort of trade-off between performance, because the smaller the time step, the longer it's going to take to run. But if there's a case like that where you really need to, get an accurate picture of what, how things are reflecting in a short pipe, you really need to use a small time step, and it's worth that, waiting that extra time. And usually it's a matter of, a couple more seconds or a minute or something, but it really depends. The larger the model, the bigger the impact. But again, we'll see this later on. There's a little dialog that helps you. It's called the transient time step options, which helps you with that trade-off of, okay, you can enter a custom time step and see the impact it has on that maximum adjustment. If you go into the pipe flex table, there's a couple of fields that you can add. Yeah, here they are. So length adjustment percent and length adjustment. So you can actually see the adjustment in feet if you're choosing to adjust the length. And that way you can even sort it or do whatever you want and maybe better assess if those adjustments are okay, if you're okay with them. If it's a matter of 10 feet or something, thinking about how fast the wave is moving, it's probably not going to make a difference. If it is at a critical point, it could still be critical as far as how it reflects off of that closed valve, and you've got your air valve next to it, and that it could be significant. If you have a case like that, then I would definitely do a sensitivity analysis. Try much smaller time step so that it's not a large adjustment. Maybe just run it for not the full duration, but just 10 seconds or 20 seconds or something that where it's not taking you all day to run it. And then compare the results. If they're pretty much the same, well then you could just go with the smaller time step increment and continue on your way there. But this is definitely a topic that pretty much everyone who's new to Hammer will ask about, so it's worth covering. As far as I mentioned, you could adjust both the length and the wave speed. So the transient time step options has the field where you can choose between them. So normally I think the default is length, which means it will be adjusting your length to make sure the wave will reach one end of the pipe to the other in even increments of the time step with the original wave speed. But if you choose to adjust wave speed, then it's going to keep the original pipe lengths and adjust the wave speed on a per pipe basis such that the same thing happens. So you could try that as well, but I think both cases you can have problems with short pipes regardless, because you can think of what you would have to do to the wave speed to keep your short pipe. Well, that's going to skew things as well. Pump technologies, a lot of pumps have new technology, but water hammer can still be a problem if they start or stop too quickly due to that line packing effect. So there's not really, you're not safe because you have a new pump, basically. And you can model soft starts with hammer to see if it's okay or not. Surge protection. Well, there's a lot of specialized valves. There's different tank or pipe configurations that could be used to protect against surges. Lots of different devices out there, surge anticipator valves, lots of different things that can be used. There's not really any one answer, and in some cases it's a matter of a combination of elements. So passive protection. So as opposed to installing a new tank or a new valve or something like that, you can do other things like work with the elevated storage tanks. You can have bypass lines around the valves. You can have pipes that are just stronger or more vacuum resistant. Active protection, it requires a lot of moving parts, which could, mean regular maintenance and potential for those things to fail at some point, and maybe even leave you with a false sense of security. So when you're dealing with passive protection, these are things that are kind of, passively there to help you. Another thing could be, a flywheel on a pump. So increasing the momentum of your pump by putting a flywheel on it, that can make it so that when it does shut down, the time it takes for it to fully spin down is increased, so that it's not stopping your water column so fast. So that's something that can help. And then also, obviously, a well-informed staff is definitely a good investment, because if somebody doesn't realize that they shouldn't be closing a valve so fast, that's definitely a concern. So it's in addition to all the traditional surge protection that you could put in and simulate and hammer, it's also very important to have a well-trained staff. So conclusion for that: so risks should not be ignored. It's well worth doing a transient simulation. Using Bentley Hammer is a worthwhile investment. It's really it's absolutely worthwhile. Transient simulations can be complex. It's not like a WaterCat or WaterGems where you just put in some basic information, and maybe you can simulate a connection to an existing system with like a pump and a reservoir or something, and you can kind of get the pressure results you need pretty quickly. With Hammer, because of how complex these things are, it's that much more important that things are modeled exactly the way they are, and that you've got accurate diameters and elevations. It's that much more important in Hammer, because things are so sensitive to that. And lastly, there's not really any safe practice or rule of thumb. It's really not worth just running through the Joukowsky equation and okay, I'm good. Sometimes there are things that you may not realize will be happening, and complex interactions that can occur that you may not realize, and if you don't do a transient simulation, then you could be putting your system at risk. Also, sometimes, again, you may see some strange results, or results that look strange at first glance, but you really have to dig in there and animate those profiles, really think about what's going on, and how this is happening, because sometimes the results can be counterintuitive. You can see some interesting things, but results should be reasonable in a physical sense. So the focus of Hammer is to get practical conclusions, not really to fuel academic debates or academic papers. It's very much a practical tool.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.